Okay, so another question for the week for tutorial, which is going to be about the sheet metal bending. So the example we have is a sheet metal blank is to be bent as shown in the figure 2015. The metal has a modulus of elasticity of 205 megapascal, the yield strength of 275 megapascal, and the tensile strength of 450 megapascal. We need to remind the starting blank size and the bending force if the V die is going to be used, with the die opening dimensions to be 25 millimeters. So in this diagram, if we're going to analyze that, we can see that dimensions here is going to be 38, we have 25 here. The radius is going to be 4.75 millimeters. The angle alpha is 120 degree. Okay, and the thickness is 3.2 millimeters. We're going to have a look about the steps of the solution. First, we need to do some analysis for the bending operation. So once again, we go back to the same figure, but still some of the important terms is going to be getting from the figure 211, which is going to be the figure above. So you can see that we do have a metal thickness going to be the T, we have the width, we have the alpha and the alpha prime. Okay, and this should be the alpha, and this is the alpha prime, where totally is going to be about 180 degree. And we have the bending radius R. The bend is going to be made over the width of the workpiece W, the width of the workpiece W. So the bend allowance as a definition. If the bend radius is going to be small relative to the stock thickness, then the metal tends to stretch during the bending. It is important to be able to estimate the amount of stretching that occurs, if any, so that the final part length will be matched with the specified dimension. The problem is to determine the length of neutral axis before the bending to account for the stretching of the final bend section. The length is called the bend allowance, and it can estimate it as following. The equation for the bend allowance, or the AB, is equal to 2 pi multiplied by the alpha divided by 360, and then multiplied by the radius plus the KABT, ABA, multiplied by the T. The AB is the bend allowance in millimeters, the alpha is the bend angle in degrees, the R is the bend radius in millimeters, and the T is stroke thickness in millimeters, and the KBA is going to be the factor to estimate the stretching. So the following design value are going to be always recommended regarding the relationship between the R and the T. So if the R is less than 2T, then the KBA is equal to 0.33. If the R is more than or equal to 2 times the T, then the KBA is equal to 0.5. The values for the KBA is predicted that the stretching occurs only if the bend radius is going to be small relative to the sheet thickness. We have the spring back, which is something like we still having some elastic energy within the part that causes it to return back to the original shape a little bit. So when the bending pressure is going to be removed at the end of the deformation operation, the elastic energy remains in the bent part, causing it to recover partially towards its original shape. This elastic recovery is called the spring back, and defined as the increase in the included angle of the bent part relative to the included angle of the forming tool after the tool is going to be removed. And the spring back can be simply calculated by knowing the value for the alpha prime and the alpha prime of T, and then we can simply find the spring back ratio. Okay, so the alpha prime is the included angle in the sheet metal part, degrees, and the alpha prime T is going to be included angle of the bending tool in degrees. Also not as obvious, an increase in the bend radius also going to occur due to the elastic recovery, and the amount of the spring back is going to be increases with the modulus of elasticity and the yield strength of the work metal. Okay, the other term we have is the bending force. which is the force required to perform bending, depends on the geometry of the punch and the die, and the strength, the thickness, and the length of the sheet metal. So the maximum bending force can be estimated by the means of the following equation. The force is equal to the kpf multiplied by the ts multiplied by w multiplied by t squared divided by the d, where the F is the bending force in Newton. We do have the T as tensile strength of the sheet metal in megapascal. W is the width of the part in direction of the bend axis in millimeters. The T is stroke thickness in millimeters. And the D is the die opening dimensions as defined in the figure 2014 in millimeters. So that's the D. Okay, that's the D. Then on top of the die we have. So this equation above is based on the bending of the simple beam in the mechanics, and the kbf is constant that accounts for the differences encountered in actual bending processes, and its value usually going to depend on the bending type we have. So the V bending, the kbf is going to be 1.33, and for the edge bend is going to be equal to 0.33. So let's go back to the example once again. So let's see what do we have here. We have the modulus of elasticity given to us. We have the yield strength, and we have tensile strength. Also, we do have all the dimensions, including the R and the alpha. So let's see how we can find the starting blank size and then the bending force if we are using the V die for the bending. So highlighted the given parts to us, and then we start to apply the equation. So I start with the step number 1. The starting blank have 44.5 millimeter width. Yeah, that's the width here. Okay, and its length is 38 plus the 25 plus the AB in between them. For the including angle alpha prime is equal to 120 degree, and the bend angle is going to be 60 degree. How we got the 60 degree? Because we have the alpha plus the alpha prime is 180, so the difference between them is going to be 60 degree. Now the value of the KAB for the V type is equal to 0.33. Since we have the R over T is equal to the 4.75 divided by 3.2, which is thickness, radius divided by thickness, and this will be equal to 1.48, which is less than 2. So the calculation for the AB is going to be equal to 2 pi multiplied by the alpha divided by 360 plus multiplied by the R plus the KBA multiplied by the thickness. So for these parameters we have the alpha is known as 60, the R is 4.75 millimeters, the KBA is 0.33, and the T is equal to 3.2 millimeters. So we apply the figure to the equation, and the AB is going to be, in that case, 6.08 millimeters. Done. We found that the length of the blank is going to be equal to 38 plus 6.08 plus 25, and this will make it as 69.08 millimeters. Of course, the width of that part is going to be the 44.5 millimeter that we have as a width. Now we're calculating the force for the bending. Now we're using the V type, so the kbf is going to be equal to 1.33 as we mentioned earlier. And the equation here saying that kbf is known, the TS or tensile stress is known, the width is known, the thickness is known, and the D value is known. So we put all the parameters in, and we will get that the value for the force is going to be equal to 10,909 Newton. So that's it for this question, and we are going to move to the next question soon.